much. So it's my great pleasure to join, although remotely, the IUCAA summer school this year. It's a pity that I cannot be there in person, but at any point, feel free to interrupt me and ask me questions. So I don't want this to be like a Zoom talk. I want it to be as much interactive as possible. So let me share screen. All right, I hope you can see my screen. Yeah, so I'm Debarati Chatterjee. So I'm associate professor at IUCAA, and I'm also chair of education and outreach for the LIGO India project. So during these last few weeks, I hope that you enjoyed listening to lectures on general relativity, on gravitational waves, as well as stellar evolution. So this lecture will already use the information that you have, the knowledge that you have acquired in this previous lectures, and try to connect it with something which is quite a topic of current research, and this involves compact stars and um, how we can know more about compact stars from gravitational waves. So so what are compact stars? So I'm sure you also heard about this in the stellar evolution lectures. So we are talking about uh, these objects over here, which are produced at the endpoint of evolution of massive stars. So normal stars like our sun go through this branch. So the low and medium mass stars go through this upper branch, and they end up as white dwarfs. And on the other hand, high mass stars go through another branch, and depending on their initial mass and also the kind of process they go through the supernova process, they may end up as a neutron star or as a black hole. So as you know that these are extremely elusive objects, so we only know about them not directly from they do not emit radiation in the visible range. So they have been elusive for a long time. However, we already have had theoretical predictions about the existence of these kind of objects. So white dwarfs typically have masses around 0.04 to 8 solar masses. Solar mass is the mass of the sun, of course. Neutron stars, they start with and they end up from the evolution of massive stars, the progenitor stars with a mass of 8 to 25 solar masses, whereas black holes are the end point of evolution of even more massive stars, so which have the progenitor stars which have masses above 25 solar mass. So why do we call them compact stars? So of course, I'm talking about compactness here. So compactness is defined as in dimensionless units as the ratio of the mass to the radius. So if you compare the compactness of these objects that I'm talking about, white dwarfs and neutron stars, and if you compare them with the compactness of the Earth and of the Sun, this is something that is a back of the envelope calculation that you can check by yourselves. And you can see that the compactness is much higher. So for the Earth, while it is around 10 to the minus 10, for the Sun around 10 to the minus 6, for white dwarfs, this is in the range of 10 to the minus 4, while for neutron stars, you can see that they are extremely compact. So they are very relativistic objects, and they have compactness in the ratio of 0.1 to 0.3 in the dimensionless units. One can also calculate the surface gravity of these objects, which is the mass divided by r squared, or the mean density. So typically, I will come to the I will come to the structure of compact stars in a few slides. So as you can see here from these back of the envelope calculations, that the mean density of these objects is also extremely large. So compared to laboratory physics, these are regimes that are inaccessible. So this is why we study these kind of objects, because um, these compact stars are essentially astrophysical laboratories that allow us to study matter which is so extremely dense. Okay, so here the masses and radii have been given in kilograms, and the radii in kilometers. So white dwarfs have masses around 0.5 to 1 solar mass, neutron stars 1 to 2 solar mass. And white dwarfs are quite large actually, although they are called dwarfs, but they have large radii, so around 5,000 to 10,000 kilometers, while neutron stars are much more compact, so they have radii of around 10 kilometers. So from these, you can, of course, estimate the compactness, surface gravity, and mean density. And so you can check for yourselves that why we call these compact stars and why they have such large mean densities. So I am sure you have also heard about this in the previous stellar evolution lectures, but so we can have a quick recap of what is the process through which normal stars go through in order to produce white dwarfs and neutron stars. And this is actually a very, very interesting astrophysical process, because this is involved with different multi-messenger signals that you can actually observe with telescopes. So normal stars, so for example, even our sun, so these, we can see these stars because they generate thermal energy by fusing through nuclear fusion of light elements, typically hydrogen, producing helium. So the structure of these stars is basically determined by the balance of their thermal pressure supporting their collapse due to gravity. So these two, the thermal pressure and the gravitational attraction, they basically balance each other. That is what determines the structure. Now, when the hydrogen fuel in the core becomes exhausted, now there is no more thermal pressure support to support these stars against gravitational collapse. So what happens is that the core starts to contract under gravity, and the temperature is raised, which initiates helium production, helium burning to produce carbon. So now we are going from hydrogen, helium to the next higher element, carbon. Um, so in stars like light stars like our sun, this process ends here. Basically, it ends up, as you can see here in the cartoon at the bottom, that this process ends when carbon oxygen is produced at the center and ends up as carbon oxygen white dwarfs. But when you go to much more massive stars, this process can continue. So producing higher and higher, higher and higher elements in the periodic table. And so this process continues from fusion of carbon to oxygen, neon, magnesium, silicon, iron, and so on. And it forms this onion-like layered internal structure. So, so how long can this continue? So this is a question that we ask ourselves, but the answer is given by laboratories which tell us that the binding energy of iron element is actually the highest, which means that beyond iron, fusion cannot take place anymore. So this branch, as you can see, so this is the binding energy per nucleon as a function of mass number. So hydrogen, helium, lithium, and so on, oxygen. So this continues, the fusion continues to produce more and more bound elements. But beyond iron, as you can see, that the binding energy goes down. So this is something we already know from laboratory experiments. And so this also tells us that this is the limit of fusion processes in the stars. So once the fusion ceases, so there is no more thermal pressure support, and beyond this point, the core has to collapse because it is no longer supported by thermal fusion, by the thermal pressure. So this results in a very phenomenal, a wonderful phenomenon, which is called the core collapse supernovae. So what happens is that these outer layers start to collapse towards the center. This shrinking causes the core to heat up, and this again results in photodisintegration of the iron nuclei, forming helium nuclei and neutrons. You can also see this process here. And the helium nuclei are also split into protons and neutrons through photodisintegration. So all these processes happen during the implosion. And as the core density increases, now it also becomes energetically favorable for electrons and protons to combine through a process called electron capture. And this results in production of neutrons and neutrinos. So basically, the core ends up becoming neutron rich. Um, in beyond this, actually the process that we are describing here is not very simple, because this involves many complicated processes. Some of these are even under current investigations, because they go through many different processes like instabilities, shocks, and so on. But the overall picture can be summarized like this, that the neutrinos, which were produced in this process that we talked about here, so these neutrinos are almost non-interacting, and they escape freely from the core and take away the energy. So what happens is the collapse is now accelerated towards the center. Therefore there is nothing that can support the collapse of the star unless there are strong nuclear forces. So this is something that I will come to explain in the coming slides. So if once this collapse halts because of strong nuclear forces, the infalling matter now rebounds. So there is a bounce at the surface where the nuclear densities are reached, and this produces a shock wave which propagates outwards. So this shock basically plows through the material and dissociates all the heavy elements in the way, and effectively this could stall the explosion. So this is actually a problem that astrophysicists have been working on since several decades now. And so the idea is that the neutrinos from the core, which contain thermal energy, so they can revive the shock and cause the supernova to explode. And as you can see here in the picture, there are, if you go to the NASA website, for example, you will see beautiful images of these supernova remnants that can be seen. So, like I said, again, the process is not as simple as I described here within a few bullet points. There are many other processes like standing accretion shock instabilities and so on, which researchers are still probing with the help of hydrodynamic simulations. So now the interesting question is, what is the entire star dispersed into the interstellar medium, or what is left as a remnant in the center of a star? So the answer is that there is a degenerate remnant that is left behind in the core collapse supernova explosion. And that, what I told you earlier, is something that is neutron rich because of the process that I told you about earlier, the electron capture process. So this neutron star, when it's initially born, it's basically extremely hot. So it's also called a protoneutron star. But this basically starts to emit neutrinos, which take away its energy, and the star cools down and forms what we observe as a neutron star. This core collapse supernovae, again, depending on the initial progenitor star, it can end up as a neutron star. But if the progenitor star, like I said earlier, if it is even beyond 25 solar masses, if it is that heavy to start with, then the mass of the remnant is so high that this also collapses into a black hole. So now we talked a little bit about the stellar evolution. I'm sure you heard about this also in the previous lectures during the summer school. So the idea is that depending on the progenitor mass, there are these different kind of compact stars that can be produced: a white dwarf, a neutron star, or in the extreme case, a collapse into a black hole. So here is, I hope you can see the animation. So here is an animation of this kind of process where the star is burning fuel in its interior. And during the stellar evolution process, it's thermal energy supporting it. But when I can show this again. So here, as you can see, the stellar structure is determined by the thermal pressure balancing the gravity. But once it goes, the fuel is used up in the interior, then the outer layers, like I said, they first they implode. There is a bounce at the nuclear surface, and there is a shock which explodes the material into the interstellar medium, and what is left behind at the center is a rotating neutron star. So again, depending on, so earlier I already told you that these compact stars have different masses and radii, and so also their interior composition is different. Their interior densities are different, and the composition is also different. Typically, so I'm talking about carbon oxygen white dwarfs, like which would also be the end point of evolution of our sun at some point. So there is basically a very thin hydrogen shell, a helium shell, and inside this there is the majority of the white dwarf is formed by a carbon and oxygen core. A neutron star structure, on the other hand, is much more complex because it encompasses densities that go all the way from nuclear densities at the surface up to several times, up to 10 times nuclear densities in the core. So it means that the kind of material that we observe in nuclear experiments, this is something that is relevant only to the very outer layers of the neutron star. But as we go towards the interior, the densities increase and you encounter different material. Like, for example, the outer crust, you have ions and electrons. As you go towards the interior, you encounter an inner crust, which also contains neutrons in addition to ions and electrons. Then at a certain point, you encounter the outer core, which consists basically of a sea of neutrons, protons, and electrons. Mostly neutrons, that's why we call it a neutron star, but a small fraction of protons and electrons. While the inner core, where the density is beyond 2 to 3 times saturation density, going up to 10 times, this is where we need to resort to theoretical models, because this is a regime that is completely unknown to terrestrial experiments. So I had only briefly told you about the fact that in the case of if there is a nuclear if there, like when I was talking about uh, let me go back here. Yeah, so I was telling you about the collapse in massive stars, that it can be halted by strong nuclear forces. And so let me explain what these nuclear forces are. So like I said, there is this process of electron capture that happens inside the collapsing star. So protons, electrons combine to form neutrinos, and the electron neutrinos freely stream out of the star. Now, the neutrons and protons are basically, okay, let me go back to this slide. So electrons and neutrinos basically have half integral spin. So these are also called fermions, okay? While so there are different kinds of particles in particle physics, which are defined by the kind of spin, the fundamental spin that they have. So the electrons and neutrinos that form the neutron star, they are basically, or electrons are forming the white dwarf as well. So they are fermions, and the typical behavior of fermions is that they obey the Pauli exclusion principle, which means that if you in dense matter, if you try to squeeze fermions, they repel each other because they do not want to be forced into the same energy level. This is in contrast to the other type of particle called bosons, where bosons can all in the lowest and can go to the lowest energy state, something that is called condensation. This does not happen in the case of fermions. So these fermions are basically forming white dwarfs and neutron stars. So what happens is that when the density is increased, the fermions are forced to take up higher and higher energy level. That means that this results in some kind of a pressure, and this is called the degeneracy pressure. And this degeneracy pressure is what now supports this collapsing star from collapsing completely into a black hole. So in the case of white dwarfs, it is the electron degeneracy pressure that supports the star. In the case of neutron stars, it is the neutrons that provide the support. So as you know, electrons are much lighter than neutrons. So in the case of white dwarfs, this happens pretty early. So the light stars can be supported by this mechanism. In the case of massive neutron stars, in the case of massive progenitor stars, even electron degeneracy pressure is not enough to support the star against collapse. So in that case, one needs the neutron degeneracy pressure. But like I said, for very extremely heavy stars, even that is not enough to support the star from collapsing, and it collapses into a black hole. So so this is something that is, again, I said fermions, this behavior of fermions, that they obey the Fermi-Dirac, the Pauli exclusion principle, can actually be also explained with the help of statistical theory. So fermions are said to obey the Fermi-Dirac statistics, which mean that at zero temperature, they have a certain kind of so if you look at the probability density, so if you look at the probability of the particles, so there is a certain energy called the Fermi energy, up to which all the levels are filled for these particles, whereas beyond that particular energy level, beyond the Fermi energy, there are no other levels that are filled. So this probably several of you have already learned about Bose-Einstein statistics and Fermi-Dirac statistics before. So this is the zero temperature situation, and we can consider neutron stars actually to be cold objects, and the reason is that the energies of the constituent particles are the masses, the temperature of the star is actually much less than the energies of the constituent particles. That's why it can be considered to be zero temperature. So now if we want to actually calculate the pressure now starting from this statistical theory, so what we want to calculate is the number of states at a given momentum per unit volume. Okay, so let's call this as dn, and for a given momentum k, so here for example in the momentum space we can define these filled levels as a Fermi surface. So imagine a sphere within which all the levels are filled out. So this is called the Fermi sphere, and the surface where these are filled is called the Fermi surface. So now we want to calculate the number of states at a given momentum k per unit volume. So we can write this down as dn, which is d3k divided by 2 pi h bar cubed. So this is coming from the from this Pauli exclusion principle. So you know that d3k can also be written as 4 pi k squared dk if we integrate over the angle. So now using this, one can actually write down the equation of state of a star. So whether it's a white dwarf or a neutron star. So as you know that equation of state of in general of a perfect gas, for example, is the relation between its pressure, its density and temperature. So in the case of compact stars, the temperature can be assumed to be zero, like I said. So in that case, we want to derive a relation between its pressure and density, or its alternatively also its pressure and energy density. And this is something that can fundamentally describe every property related with the compact stars. So in order to derive this, we again apply the Fermi-Dirac statistics. So we start with the number density. So what we wrote down in the previous slide, and we integrate over it. So what we get is actually a relation between the number density and the Fermi momentum. So one can write down the Fermi momentum in terms of the number density of particles. So one can actually show that from the number density, if you actually integrate over the energy, instead of dn, you integrate over the energy, then you can also calculate the energy density, which is the total energy per unit volume. And this can be also very easily related with the Fermi momentum. Once you know the number density and energy density using first law of thermodynamics, so this is one of the basic laws of statistical mechanics also. So basically the pressure can be written down in terms of the number density and the energy density. And this is also called the Gibbs-2m relation. So from this, effectively it's the first law of thermodynamics, one can derive the pressure. So this relation between the pressure and density, or pressure and energy density, is what we call the equation of state of a star. So there is an easy way of actually parametrizing this with the help of a polytropic equation of state. So let's say that we write down the pressure P in terms of the density rho in such a way that P is a constant K times rho raised to the power of gamma. So gamma is an index. So it can also, sometimes it is also written as 1 plus 1 over n for mathematical convenience. So this is nothing but a polytropic index. So this is a parametric form of describing the relation between the pressure and the density. Sorry. So it can be shown that in the case of non-relativistic electrons, so this I'm talking about electrons, so this is relevant for white dwarfs. So for the case of non-relativistic electrons, this relation between P and rho is such that the pressure is related to the 5/3 power of the density. Whereas for a very relativistic case, and this is when the Fermi momentum is much larger than the electron mass, in that case, the pressure can be shown to go as density to raised to the power of 4/3. So this is actually a very easy parametric way of describing the equation of state of a white dwarf, for example. So say now that we have an equation of state that describes the behavior of the matter in a white dwarf, we want calculated structure and see whether we can actually compare it with the actual observations and see whether we can explain it. So in order to do that, this is a Newtonian calculation, because for white dwarfs, the Newtonian calculation is more or less enough for practical purposes. So this is actually quite simple in the case of white dwarfs. So you have to equate, so here also in this cartoon, you can see that you have to basically equate the pressure of the star, the pressure gradient, with the gradient of the mass, which means that you basically balance the pressure of the electron degeneracy pressure against the gravitational attraction. So that means that there are these couple of equations that you need to solve consistently. So this can be done numerically as well. So you start from the center of the star where the radius is 0. Then you go on integrating outwards. So for each shell dr, you can calculate the increment in pressure and the change in the mass as well, until at a certain point the pressure is actually largest at the center of the star, and then it decreases towards the surface. So at a certain point where the pressure drops to a very low value, that is where we call it the stellar surface. So this equation, this set of equations actually requires now this relation between P and rho that we defined as the equation of state. So once we have the equation of state, we can easily integrate over these structure equations and obtain the mass, radius, the structure properties of the neutron star, of the white dwarf. So um, yeah, so basically, one can also do this analytically for some simple cases, and this is called the Lane-Emden equation. So you can see here that this same equation can be written in terms of some dimensionless quantities, and one can solve them on the computer in order to get the Lane-Emden equation. So here some interesting cases can be looked at. So the non-relativistic limit, if you take gamma equal to 5/3 that we talked about, in that case, one can see that this m times r cubed becomes constant if you put 5/3 over here. If you take gamma less than 4/3, then the sphere is unstable. If you take gamma equal to 4/3 here, you will see that m becomes constant. So this is the limiting case of stability. So now we want to actually compare with observations and see, is this what we actually get? So in order to do this, basically one uses the luminosity of the white dwarf. And from that one can, if one can measure the effective temperature, then one can obtain its radius. And if there is a white dwarf which is in binary with another companion star, one can also determine its mass. And from basically from the mass and radius, we can compare with the structure properties that we derived. So historically, it went like this. So first, Sirius B was the closest and brightest white dwarf that was observed in 1925. And the theory followed soon after in 1926 from Dirac and Fowler. So they obtained this Fermi-Dirac statistics that I talked about and applied it to white dwarfs. And they said that this electron degeneracy pressure supports white dwarfs against gravitational collapse. Now, the maximum possible mass for the non-magnetized white dwarf was calculated by Chandrasekhar, and this was shown to be 1.44 solar mass. So here you can see this mass versus radius plot of the white dwarf, and this was obtained by Chandrasekhar back then. This faced, so what Chandrasekhar had proposed was that for masses in excess of the Chandrasekhar limit, the electrons should become relativistic. And therefore, degeneracy pressure would be insufficient to balance the star's gravitational attraction. And so he predicted that in that case, it would collapse to a black hole. And at that time, this faced a severe criticism from Arthur Eddington, but Chandrasekhar won the Nobel Prize in 1983 for this magnificent work. Later on, there were also many corrections added to this mass radius relation coming from Coulomb correction, thermal effects, magnetic fields, and other complexities. Now, the similar history also continued with neutron stars, but in the case of neutron stars, this was more interesting and more complex. So first, Chandrasekhar showed that massive stars will collapse. And so Landau wrote an article about maximum mass of neutron stars back in 1931. Soon after 1932, Chadwick had discovered the neutron. And so then Barbie and Zwicky, they introduced the concept of neutron stars with the help of these neutrons, composed of these neutrons, in 1933. And a few years later, in 1939, Oppenheimer and Volkoff computed the mass of neutron star using the this balance of like the stellar structure equations that I showed you. So this is also called the Tolman-Oppenheimer-Volkoff equation in the case of neutron stars. So as we already, most of us already know that soon after 1967, Jocelyn Bell discovered pulsars. Until then, people did not know that these were actually rotating neutron stars. But in 1968, Gold and Pacini proposed the lighthouse model, which said that pulsars are nothing but rapidly rotating neutron stars. Now we know that there are multi-wavelength astrophysical observations. So this discovery was made in radio waves. But as we know that now not only radio waves, but neutron stars can be observed across the electromagnetic spectrum, also from X-rays to gamma rays to infrared radiation. which gives a lot of information about these objects. Now, neutron stars can be either isolated or in binary. So it means that when they are powered by this electromagnetic radiation, we call them rotation powered. If they are accreting material from their companion, we call them accretion powered. But the accretion powered pulsars also go through an evolution in binary and may result in millisecond pulsars. So again, I don't want to go into the details, but there is an explanation of this with the help of the lighthouse model, how the electromagnetic radiation is produced in pulsars. But what it also tells us is that neutron stars have a dipole magnetic field. So if you use that dipole formula, so one can actually relate the magnetic field with the period and the period derivative of pulsars. And these can be plotted as you can see here. So most of the pulsars actually fall here in this swarm in the middle that you can see. But also with more and more observations, we identified more and more species of neutron stars. So here, for example, these are pulsars in binary. And on the other hand, you can see these objects which are lying at high P and P dot, which mean that they have correspondingly very high magnetic fields. These lines correspond to increasing magnetic fields. So these species are also called magnetars. One can also determine from this relation the age of the pulsars, their breaking index. So what that tells us also about what is the mechanism going on inside neutron stars, how they are spinning down, and so on. Like I said, there are many other objects that are related with neutron stars, magnetars, central compact objects, isolated neutron stars, rotating radio transients or RATs, fast radio bursts, and so on. So there is a zoo of particles out there, so a zoo of compact stars out there which are related to neutron star evolution. Now, from all these observations, one can actually derive a number of different astrophysical observables, such as its mass, its radius, spin period, and so on. So from these observations, we can actually say a lot about their internal properties. So in general, if neutron stars are in binary, so you know that for binaries, one can determine their Keplerian parameters. But since neutron stars are extremely relativistic, one can also determine the post-Keplerian parameters. And from that, one can accurately determine their masses. So there are all these different post-Keplerian parameters which are related to their masses. So if these are measured, then one can determine from the crossing of these parameters what is the mass of this component neutron stars in the binary. So here is a list of compilation. This is an older one from these different kind of binaries. You can see that the error bars are larger for the case of white dwarf neutron star binaries or X-ray binaries, but double neutron star binaries, the errors are much smaller. Again, there are other ways to determine the masses and radii. For example, gravitational redshift can be determined from spectra of neutron stars, and this gravitational redshift is related to its mass and radius. Similarly, neutron star cooling, if one can measure the flux and luminosity, one can determine its effective temperature. And from that also, if one can determine the gravitational redshift and the mass and radius as well. So most of the radii actually are not as well determined as the masses, and the reason is that these are determined from direct emissions from the neutron star surface, and these have a large number of uncertainties like radius estimates, which are affected by distance uncertainties, then dispersion measures which have large ambiguities, and so on. So radius measurements are not as good as the mass measurements. Recently, this has improved with the nicer mission, which is the Neutron Star Interior Composition Explorer mission from NASA, which started to observe rotating hotspots, and with the help of by modeling general relativistic effects of pulse profiles, they are able to determine radii to up to 5% accuracy. Again, moment of inertia is something that is also related to mass and radius squared, and this can also be derived from the from spin orbit coupling and precision and other things like that. So, like I already said, once you have the equation of state, you can calculate the structure of neutron stars with the help of the general relativistic version of the hydrostatic equilibrium equations. These are also called Tolman-Oppenheimer-Volkoff equations. Now, what this tells us is actually when this was first done for neutron stars composed of pure neutrons, then it was seen that the masses obtained from these calculations is actually very low. So, what was missing in this ingredient? So, first, people considered that maybe it is the fact that electrons and neutrons are not considered. So, charge neutrality chemical equilibrium was taken into account to correctly model the interior of neutron stars. However, it was found that the masses were not compatible with 1 to 2 solar masses that are actually obtained in observations. So, what is missing from this free Fermi gas picture? What is missing is actually the nucleon-nucleon interaction, which means that this is one of the major ingredients that can which can support neutron star masses as large as 1 to 2 solar masses. So this indirectly tells us that neutron stars are a way to study fundamental constituents of matter. This is something that gives us an idea of nuclear interactions in neutron stars. But just to give you an idea that this is different from what you actually get from other kinds of terrestrial experiments, because this is a figure which plots the temperature versus densities. And you can see here the terrestrial experiments actually study matter which is hot and dense, and also with the same number of neutrons and protons, whereas compact stars lie on another axis where the number of neutrons is much greater than number of protons, and they are also at zero temperature. So there has to be theoretical modeling in order to predict the neutron star interior. So also particle accelerators tell us that neutron stars should also have strange particles inside them, some particles that can only be seen for a short fraction of a second in particle accelerators. So these compose the inner core. So this is a very complex physics that needs to take into account nuclear physics, particle physics, condensed matter physics, and so on. And once you have the equation of state and astrophysical equation of state, you can actually connect them with astrophysical observables. So I will skip these slides. So these are about some more complexities. So what I come to in the last few minutes is that the breakthrough has come recently with the discovery of gravitational waves. And the reason is that neutron stars can actually emit gravitational waves through many different mechanisms like flares and outbursts, and also different oscillation modes that can be active inside neutron stars. And all of these, the gravitational wave emission actually depends on its interior composition. So this is something that is analogous to heliosismology or to earthquakes on the Earth, and these are called. This field is called neutron star astroseismology. But of course, the existence of gravitational waves was first shown by Hulse and Taylor back in 1974 when they were observing a binary of neutron stars that were slowing down and following exactly the trajectory predicted by general relativity. And so this was this led to a hunt for gravitational waves This has already been described to you in previous lectures. And the first direct detection came in 2017, not only in gravitational waves, but also in many other frequencies, so which tells us a lot, gives us a lot of information about their interior. So this is the beginning of the era of multi-messenger astronomy, where we can use information at multiple frequencies in addition to gravitational waves. And what is very surprising is that these neutron stars, while they are merging, the merger of neutron stars, such as in this 2017 discovery, these this tidal deformation of the neutron stars in the binary also give us a lot of information about their interior composition, because they are also related to the mass and the radius. So this is the story so far of gravitational waves. So there have been many discoveries of neutron stars, compact stars, and black holes. As you can see here, the yellow ones are the neutron stars obtained in electromagnetic radiation, and the red ones are, sorry, the orange ones here are obtained from gravitational waves. And so already this is opening up new questions as to how large the neutron star masses can be, and whether or not there is a mass gap between the highest observed neutron stars and the lightest black holes. So I think I will stop here, and so feel free to ask me questions about this lecture. And um, I don't know if we still have time for a few questions. I will keep my slides on because for referring to them. But are there any questions from the summer school participants or from the refresher course participants? I don't see any questions. Um, any question from the online participants?
What should can you hear?
Sorry, once again.
Were you able to hear me?
Yes, I can hear you now.
What should be the the value of compactness to consider the electron to be a relativistic manner?
Okay.
Like at what point we will consider it to be relativistic?
Yeah, actually, whether or not it is relativistic depends on, like I said, so this depends on whether or not the Fermi momenta that you are considering for the particles are less than the constituent mass of the particles, or whether they are greater than them. So that this is something that defines the definition of whether they are relativistic or not. But
Anything to do with compactness of the neutron star?
yeah, so actually, well, the non-relativistic electrons, so if you plot these, so the you can see here, so pressure and density in terms of say log p and log rho, so you can imagine that you will have a different slope for the pressure and energy density. So correspondingly, if you have a neutron star which has a steeper gradient, that means that the equation of state is called stiffer. and that corresponds to a higher mass object. So that can support a steeper slope actually supports a higher mass. So this is something that can be shown by solving the hydrodynamic equations. So that way you can imagine, like if you have two equation of state curves with different slope, so whichever is stiffer will actually have a support a higher mass to a given radius.
My head, you are asking about this compactness, right? So you can see that this Kf Harvey momentum is related to N, right? So density. So if a larger the compactness, larger will be the N. So that way you can see that for larger N, Kf will be larger, and when Kf is much greater than M, then you can say that there are ultra relativistic electrons or electrons or whatever.
Thanks.
Does that answer your question?
Thanks. We got it.
Okay.
Ma'am, in the first slide, you had shown you showed the mass of the white dwarfs to be somewhere, I think, less than 8 solar masses around. But doesn't
Okay.
the Chandrasekhar limit put it at 1.4?
So this one you mean? Yeah. So here I put like the average mass of the neutrons, of the white dwarfs. Here I was talking about, probably I misquoted here. So these masses that I'm talking about are the progenitor masses from which you end up in different compact stars. So 0.04 to 8 solar mass are the light stars. Like for example, our sun also falls in this range, and these end up as white dwarfs. Higher mass 8 to 25 end up as neutron star, and this other branch higher than 25 solar mass progenitors end up as black holes. Here I'm quoting the average masses of neutron stars, so around 0.5 to 1 solar mass. So this is a mass of a white dwarf that is within this radius. Neutron stars 1 to 2 solar mass within this radius, and so on. And when you actually see the mass radius curve, this is where this is actually um, the actual relation. When you do the full calculation of the equation of state and then solve the relativistic hydrodynamic equilibrium equations, or so you will obtain a relation between the masses and radii. So you can see here that this shows that there is a maximum limit to the mass supported by a white dwarf, and this was obtained by Chandrasekhar. Again, this is the Newtonian limit. If you add relativistic corrections to it, this changes slightly. It affects only the this highest part of the curve, so it bends slightly, and this changes drastically if you add magnetic fields. So this was the original study, but this picture is much more complicated. When you add magnetic fields, then this simple picture is not valid anymore. But yeah, this is more or less the general idea.
You said that the POV equation was solved in 1939 for the neutron star to obtain a maximum mass.
Mhm.
The equation of state was used for that.
Yeah, so this is what I was trying to explain in this story. So first, what first people did was they took a free neutron gas to start with. So they said neutron stars are composed only of neutrons. So in that case, if you just take a free Fermi gas of neutrons, you solve the Fermi-Dirac equation, you get like a polytropic equation of state, you solve these structure equations, and what they obtained to their surprise was that the masses were much lower than what you actually see. You see 1 to 2 solar mass. I mean, in those days, it was not 2 solar mass neutron stars were not yet found, but at least they were 1.4 solar masses. And this does not explain. So this free Fermi gas of neutrons cannot explain how it can support a massive star like that. So in that case, people thought, okay, then let's add chemical equilibrium, because in general, neutrons are unstable with this lifetime through this electron decay, through this beta decay process. And in that case, even calculating this, taking into account that there will be a small amount of protons, electrons, even taking this into account did not change the results. So the major idea, so you can see here that this is the kind of equation of state they were originally considering, that it just has neutrons, or the main contribution is coming from free Fermi gas of neutrons with a small number of protons and electrons, but this does not support it at all. So the major fraction, the major missing fraction is actually coming from the unknown nucleon-nucleon interaction. This is why the neutron star interior composition is still an open question, because we do not know the nucleon-nucleon interaction at such high densities.
Thank you.
I don't see any other questions. Yeah, also, if you want to ask me more questions about compact stars or gravitational waves, I will be back in IUCAA in a few weeks. So if you are still around, you can drop by my office and ask me more questions. Feel free to do so. Okay, so yeah, maybe I will stop here since I don't see any other questions. All right, so I hope you enjoy the rest of the summer school, and yeah, also feel free to write to me if you want to reach out. It's my first name, Debarati, Debarati at iucaa.in. All right, so I think I will stop here.
Oh, yeah. Yeah. But it also what would you say about that?
That is what for me the girl asked
That's only true.
the temperature.
Severe.
No. Even cables are we are the same mode and so cable is not the temperature I think all the fish factors. Just assume that temperature is zero. I didn't understand.
I thought he said I will come to this why
Answer because this happens we consider